Welcome back. In the last video, we just finished working through example 9. I'm going to go ahead and just put a, whoa, don't know what happened there. I want to draw a star next to example 9 because I think it's a really good example. So review that, and, or if we're good, we're going to keep going. So example 10. Avery serves a volleyball at an angle of 35 degrees with the horizontal and with an initial velocity of 50 feet per second. A, write the component form. Write the component form of the initial velocity. So, pause the video right now. Take a minute. See if you can do that on your own. Pause. Alright, assuming you've already paused and tried this on your own, let's go over it. So, I'm going to draw a picture. If she serves a volleyball at an angle of 35 degrees with the horizontal, so this would be 35 degrees, initial velocity of 50 feet per second. That's the magnitude of her initial velocity vector. So we're going to say v sub 0, which is the initial velocity, is, again, the magnitude, 50 times cosine of 35, because that's its direction angle, 35 degrees, comma, 50 times sine of 35 degrees. Which if you then punch that into your calculator should give you decimal approximations of about 40.96, comma, 28.68. And again, what are these numbers? These are both in feet per second. Feet per second. So the ball is traveling about 40.96 feet per second horizontally, and it is traveling 28.68 feet per second vertically up. Now, this leads us to question B. Ignoring air resistance and spins, right? Write the component form of the velocity of the ball at t seconds after the serve. So what happens horizontally? Again, assuming there's no air resistance or spins, the ball is just going to keep moving horizontally 40 feet, 0.96 feet per second. So here's where I'm going to toggle quickly to this. Alright, so after 1 second, the ball is still moving right at a rate of 40.96 feet per second. After 2 seconds, the ball is still moving right at 40.96 feet per second. So what's happening? Nothing is happening to change the horizontal rate. However, gravity is affecting the vertical rate. How? Well, remember, our velocity is the initial velocity, so our velocity of something in free fall, moving up and down. Right? V of t is negative g times t plus the initial velocity. So the vertical rate at time t is initially 28.68 feet per second, but because my rate is in feet per second, I'm going to use g, gravity is 32 feet per second squared. So think about it, feet per second squared times time in seconds is going to give me the rate of feet per second. So after 1 second, the ball is already moving downward again, right? 28 minus 32 is a negative velocity. It's already moving back down. So thus, B, the velocity vector at time t, is given by, again, horizontally, it's traveling horizontally at a constant rate. Vertically, initially, it's going up, but as time increases, right, it's going to change and start moving down. And if you are standing on the top of a really, really tall tower and you drop something, it picks up speed as it falls, which is why you've got this times t element there. Okay? So, back to our class notes. We're going to now talk about force is a vector too. So, a vector F, right? Force is a vector. F, its size or its magnitude, right, is measured in things like pounds, lbs. So, example 11. A medicine ball is sitting on a hill with a 30-degree incline. So, if we have, here's our hill, 30 degrees. And here's our medicine ball, sitting on a hill. You must exert a force of 8 pounds to keep the ball from rolling down the hill. So what does that mean? That means you, right, would have to put your hand back here and essentially push, but not so it moves, but push so that your force this way, parallel to the hill, is 8 pounds, which means what? The ball itself wants to roll down the hill, right, with a magnitude of 8 pounds. So the question is, how much does the ball weigh? Well, what is the ball's weight? It would go directly smack down, right, straight down into the ground, right? And now you can draw this however long you want, but here's the idea. I'm going to erase that for a moment, because if I drew just this much, right, this weight gets projected onto the hill perpendicularly, remember? So if I were to draw this picture again, right, so again, this is not exactly 30 degrees, I'm exaggerating, but if I drew just a small little vector like this, boop, what you would do is you need, again, perpendicular. So if I start drawing things perpendicularly to this hill, like these are all the perpendiculars, like, oh, right there, there's my perpendicular. So this distance right here, that magnitude right there, that would be the 8 pounds right there, that short little thing there. And then my weight, I'll call this W, right? The magnitude of my weight vector is however long this blue line is. Now, what do I know about this right triangle? Well, again, if I draw it kind of short like that, it's not super easy to see, but if I draw my weight vector long enough so it at least intersects with the horizontal, and I can see I got a 90-degree angle there. If this is 30 degrees, what does this angle up here have to be? This angle here has to be 60 degrees. Oh, so I do know an angle here. That's 60 degrees. Right in there. That's 60 degrees. And in fact, if I draw, this is that's the magnitude of my weight vector. Again, projecting perpendicularly, 90 degrees. I can redraw this triangle. Let's just kind of redraw it like this. So if that's 90 degrees, if this is 60 degrees here, that means this angle down here must be 30 degrees. What do I know if I know this is 8 pounds, and I want to find the magnitude of my weight W? Again, I'm going to rotate this so it's at least a little bit prettier looking. So that's 8. This is the magnitude. How much does the ball weigh? Again, that's the weight. That's the magnitude of my weight force. If, again, I know that this angle here is 60 degrees, what do I know about a 30, 60, 90 right triangle? If the short side is 8, what does the magnitude, what's the hypotenuse have to be? Twice that. So how much does the ball weigh? The magnitude of my weight is 16 pounds. And again, if you needed to, you could use cosine of 60 degrees is 8 over the magnitude of W, and then solve for the magnitude of W, right? And maybe if these weren't nice numbers, that's exactly what you would do. So actually, it might be worth even just saying that cosine of 60 degrees is equal to 8 over the magnitude of W. So the magnitude of W, the weight, is multiply, divide. 8 divided by cosine of 60 degrees. And cosine of 60 degrees is 1/2, and 8 divided by 1/2 is 8 times 2 is 16. Cool. All right, so a heavy box containing 5 medicine balls is being pulled up a incline, a 30-degree incline, at a 45-degree angle with the horizontal. So now what does that mean? So again, it's same but different. I've got a 30-degree incline, so let's draw that again. So I've got a 30-degree incline, only now instead of just a ball, it's a box of balls, right? And again, this box has a weight going down, and it is going to slide down here, but it is being pulled up the incline. So now you are exerting enough force to move it this way, right, at a 45-degree angle with the horizontal. So if I were to there's my horizontal, 45 degrees, right? So really, it's almost like this picture here. Like here you are, right? You are pulling a rope, and you are walking up the hill, kind of like this. So here's your 45 degrees. But again, we still have the horizontal here. You're pulling it, and it says, to move the box, a force must be exerted whose component parallel to the incline is 40 pounds. So parallel to the incline, again, would be if I drew this, if I kind of cut through that 45 degrees. That is parallel to the incline. Yeah? So notice that nice, if I can drop that and make a nice 90-degree angle there. I'm going to redraw this triangle right here over here. And what do I know? I know that 40 pounds, right? Force must be exerted whose component parallel to the incline is 40 pounds. So that means this right here would be 40 pounds. This 40 pounds, right? Do I know this angle inside here? Well, I should, because if these lines are parallel, that means this 30 degrees here is also 30 degrees there. What is 45 minus 30 degrees? 45 minus 30 degrees is 15 degrees. So this angle right here is 15 degrees. So dropping that perpendicular. What is it that I'm trying to find? Determine the magnitude of the force needed to move the box. Again, let's call this force F, right? So what is the magnitude of the force I need there? Now I'm going to say, yeah, cosine of 15 degrees is going to equal my adjacent 40 pounds over the magnitude of the force, this vector force here that I'm pulling with. So that means multiply both sides, divide both sides. The magnitude of my force is going to be 40 divided by cosine of 15 degrees. And so grab your calculators, and the magnitude of that force in pounds is going to be approximately 41.41 pounds. 41.41 pounds, right? And that should make sense. You only need to exert a little bit more force than what would be needed to actually slide it perfectly up the incline. All right, 40 pounds to slide it up, 41 because you're losing some of that as you're pulling it with that rope. Okay? All right, let's quickly set up and see if we can't solve example 12. Calvin and Gabriel have ropes attached to a box and are pulling at it. Calvin is pulling with a force of 50 pounds at a direction of 40 degrees. Gabriel is pulling with a force of 35 pounds in a direction of 155 degrees. Determine the magnitude and direction of the resultant force. All right, pause the video and see if you can draw a picture for this situation. Go. Okay, assuming that you have paused the video, we're going to save ourselves a little bit of time and go straight to this. So, you're scrolling down. Here's the picture that I came up with. Right, it looks something like this. So, Calvin, 50 pounds. He is pulling at a direction angle of 40. So, what can I say the vector is? I can say Calvin's vector is 50 times cosine of 40 degrees, comma, 50 times sine of 40 degrees. Right? That's Calvin's vector. And then Gabriel's vector, right? Direction angle of 155 degrees. I can just use that. Those are his components. So the resultant vector, right? If I pull and pull, where's this box actually going to go? It's going to go somewhere kind of like this. So adding them exactly, I'm going to get a positive over a positive and a positive, so I'm in quadrant 1. So that makes finding the direction angle pretty nice. So find the magnitude and direction of the resultant force. I can say, well, the magnitude is just the, did not mean to do that. The magnitude is just the square root, okay, I give up. The magnitude is just the square root of our components squared. Again, use your exact values. So it's going to be about 47.39 pounds of force. And the direction angle, I can just say tangent inverse. Right, tangent inverse of my y component over my x component is going to give me about 82 degrees. Alrighty, that's where we will end this video.